jump right in. Sales, go buy some more books. I should probably just take those slides out. So chapter 4 is propagation.
Can you hear me?
Yeah, we can hear you.
Please stumble. They said they can hear you, but we can't hear them.
Okay.
Okay, radio wave propagation is getting.
Give me 1 sec. Let me see if I have my it's Bluetooth speakers and it's probably on 2 other devices.
Oh, hang on. Okay, I just sent George a message. Oop. Hopefully they got that message.
Hello?
Yeah, we can hear you.
But I can't hear you, so but go ahead still. I'll get myself fixed.
And he probably doesn't see the chat window. Okay. Radio wave propagation is getting from point A to point B. Radio waves propagate in many ways depending on the frequency of the wave, characteristics of the environment, and we'll discuss 3 basic ways: line of sight, the ground wave, and the sky wave. Line of sight. Radio energy can travel in a straight line from a transmitting antenna to a receiving antenna, called the direct path. There is some attenuation of the signal as the radio wave travels due to spreading out. This is primary propagation mode for VHF and UHF signals. The ground wave. At lower HF frequencies, okay, good. George can hear us now. At lower HF frequencies, radio waves can follow the Earth's surface as they travel. These waves will travel beyond the range of line of sight, the range of a few hundred miles on bands used by amateurs. Reflect, refract, and diffract. Radio waves are reflected by any conductive surface. Ground, water, and buildings. Refraction or bending occurs when waves encounter a medium having a different speed of light, such as water or an electrical feed line. Diffraction occurs when a wave encounters a sharp edge or a knife edge propagation or a corner. You need to double check email. Sure. Okay, we're good. I heard the beeping. VHF and UHF propagation. Range is slightly better than visual line of sight due to gradual refraction or the bending, creating the radio horizon. UHF signals penetrate buildings better than HF and VHF because of the shorter wavelength. Buildings may block line of sight, but reflected and diffracted waves can get around obstructions. Multipath results from reflected signals arriving at the receiver by different paths and interfering with each other. Picket fencing is the rapid fluttering sound of multipath from a moving transmitter. Tropo, or tropospheric propagation. The troposphere is the lower levels of the atmosphere to about 30 miles high. Radio waves can be reflected or scattered by clouds, rain, and density variations in the troposphere range up to about 300 miles. Temperature.
Gene, can we pause there for a second?
Sure.
The book says that if I look at the diagram on 4.4 page, troposphere is 0 to 6 miles and the stratosphere is from the 6 to 30. So are we looking at that? What is the zone where the stratosphere and troposphere are all together? Is that something that needs to be clarified, or I'm a little confused with that, that's all.
So the troposphere is anything up above from the 0 to 6, it looks like on that diagram.
Right.
And so that is where this particular propagation happens. It's down below, but it's not up above 6 mile. Temperature inversions that sometimes happen in the winter where you have the cold trapping a little bit of the heat. That's what happens. They had a YouTube video where they could see like reflections almost like the mirage, and that would trap the VHF signals and be able to get further propagation.
Okay, thanks.
Okay. Yeah, so the last line item there is that the temperature inversion weather fronts can form ducts, and it just traps it in that lower level close to the ground and bounces the signals hundreds of miles. The ionosphere, a region from 30 to 260 miles above the surface of the Earth. The atmosphere thin enough for atoms to be ionized by solar ultraviolet radiation, and the ions are electrically conductive. The ionospheric levels, get my tongue working here. Because of the varying density, the ionosphere forms layers with different amounts of ionization. Ionization varies with solar illumination hour to hour and intensity of the solar radiation. So again, this is the diagram that's on page 4-4. Higher ionization refracts or bends radio waves more strongly. The sunspot cycle. The level of ionization depends on the intensity of radiation from the sun. Radiation from the sun varies with the number of sunspots on the sun's surface. Higher number of sunspots results in high levels of ionization radiation emitted from the sun. Sunspot activity follows an 11-year cycle, and we are just at the bottom of the cycle, starting to come back up again. So our cycle hopefully will be increasing more and more. the ionosphere, an RF mirror. The ionosphere can reflect or bend radio waves back to Earth like a reflection. Most refraction of amateur frequencies occurs in the F layer. The ionosphere, RF mirror, the refraction depends, let me move this, the reflection depends on the frequency and angle of incidence. Too high a frequency or an angle and the waves are lost into space. Skywave or skip propagation is responsible for the most of the over the horizon propagation on HF and low VHF, the 10 and 6 meter bands during the peaks of the sunspot cycles. Skip is very rare on a 144 megahertz and higher UHF bands. Each ground to sky to ground trip is called a hop. Signals can take many paths through the ionosphere. Randomly combining at the receiving antenna, signals can partially cancel, creating irregular fading as the ionosphere changes. The resulting echo and flutter distort speech and CW. Fading causes data errors for digital signals. Sporadic E's and the aurora. Highly ionized patches of the E layer can reflect HF and VHF signals best on 2, 6, and 12 meters. Aurora near the north and south poles can also reflect VHF and UHF waves with a distinctive distorted sound. Meteor scatter. Thousands of meteors enter the Earth's atmosphere every day, most quite small. Daniel just joined us. Meteors leave trails of highly ionized gas that last for several seconds. Trails can reflect radio waves called meteor scatter. The best band for this is 6 meters. Mostly in the E layer, meteor scatter and sporadic E supports contacts up to about 1,500 miles. Okay, now the practice questions. And I need to move this out of the way. I can't read everything. What should you do if another operator reports that your station's 2-meter signals were strong just a moment ago, but now they are weak or distorted? And go ahead and unmute. Pop
Should
the
you
answer.
reorient your antenna?
You can reorient your antenna or yourself
Move it
just a
different
little bit.
distance. Yeah.
Yep. Try moving a few feet or changing the direction of your antenna if possible, as reflections may be causing multipath distortion. What term is commonly used to describe the rapid fluttering sound sometimes heard from mobile stations that are moving while transmitted?
Picket fencing.
Picket fencing.
Yep, picket fencing. Which of the following is a likely cause of irregular fading of signals received by ionospheric reflection? It's the random combining of signals arriving via different paths. What may occur if data signals arrive via multiple paths? error rates are likely to increase because you're getting bounces and signals up and down. Which part of the atmosphere?
Jim,
Yo,
on audio, regular audio, your ear fills in a lot of that stuff. But on the digital stuff, it just destroys it when you get multipath in there. We call it R2D2. Dip, bip, 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 bip. It happens a lot of times, and it gets to the point you just cannot understand it very quickly.
okay. Which part of the atmosphere enables the propagation of radio signals around the world?
Ionosphere.
It is the ionosphere, yep. Why are direct, not via repeater, UHF signals rarely heard from stations outside your local coverage area? UHF signals are usually not reflected by the ionosphere. Which of the following is an advantage of HF versus VHF and higher frequencies? Long distance ionospheric propagation is far more common on HF. What is a characteristic of VHF signals received via auroral reflection?
Strength.
Rapid.
Rapid fluctuation of strength.
The signals exhibit rapid fluctuations of strength and often sound distorted, correct? Which of the following propagation types is most commonly associated with occasional strong over-the-air or over-the-horizon signals on the 10, 6, and 2 meter band?
Sporadic E.
Sporadic E is correct. Which of the following effects might cause radio signals to be heard despite obstructions between the transmitting and receiving stations?
Knife edge diffraction.
Knife edge. Knife. Yeah.
Right.
Knife edge
Yep.
propagation.
Knife edge propagation.
It's going between propagation and ions.
What mode is responsible for allowing over-the-horizon VHF and UHF communications to ranges of approximately 300 miles on a regular basis?
That is the top about this, the bottom one.
Tropospheric.
Yeah.
I'm glad I'm not the only one with a tropospheric scatter tonight. What band is best suited for communicating via meteor scatter?
6 meter.
6 meter band is correct.
Now, Jim, let me stop on that one. It also happens on 10 meters and 2 meters, but it's not as often. Our guys in Anchorage found there was a higher throughput on 10, even though it didn't happen as often down on 10. But the most common for meteor scatter is 6.
Okay, thank you. What causes tropospheric ducting? That is when temperature inversions are in the atmosphere. What is generally the best time for long distance 10 meter band propagation via the F layer?
Sunrise to sunset.
From dawn to shortly after sunset during periods of high sunspot activity. Why do VHF and UHF radio signals usually travel somewhat further than the visual line of sight distance between two stations? the Earth seems less curved to radio waves than to light? Which of the following bands may provide long-distance communications during the peak of the sunspot cycle? The 6 or the 10-meter band?
Jim?
Yeah.
Back on that one, I'm having a little difficulty understanding the 6 and the 10-meter bands. If you or Daniel could explain what are the bands exactly, I'd probably get a better grasp on answering that.
300 divided by 6 is going to be 50 megahertz. 300 divided by 10 is going to be 30 megahertz. It's going to be the 10-meter band. Okay, let's go back to how fast the waves go through space and divide it by the meters and get back to the frequencies. 300 divided by 10 will give you 30. What's under the 30? What's by the 30-meter band? That's going to be 10 meters. Is 28 megahertz to 29.5 megahertz.
Okay, got it. That page, all right. I will refresh myself with that.
Yeah. That's the formula we live with when changing back and forth between frequency and bands. A band is a group of frequencies. A frequency is like a rifle shot. A band is like a hand grenade. Okay.
All right.
And so we talk about bands because it tells us how long the antenna is going to be that will talk in that range of frequencies. We can have one antenna that'll talk all through the 2-meter band. One length, that's like 19 inches, a quarter wave, 19-inch vertical antenna will talk through the whole 2-meter band. But it won't talk through the 1.25 meter band at 220 frequency, megahertz.
Yeah,
So that's why we talk about meters all the time, because it refers back to how long an antenna has to be to work well in those frequency ranges.
okay.
Yeah.
Cool.
And the reason the 6 and 10 meters work long distance in the peak of the sunspot cycle is because they're closest to the HF frequencies that normally work long distance, like 20 meters. You're not going to find 2 meters working or 440 working, 70 centimeters working. Does that help you out? Does that help you out?
It definitely did, and especially when Jim held up the chart. That's where I go back and review that chart.
Yeah, page 1-20 has band charts, but like Daniel says, we need to commit that formula to our brains because will help you design antennas and stuff too, and that'll be on the test questions later in another area.
Okay, thanks.
Why might the range of VHF and UHF signals be greater in the winter?
There's no vegetation.
Correct. Less absorption by vegetation. How might fog and light rain affect radio range on the 10-meter and 6-meter bands? Fog and light rain will have little effect on these bands. What weather condition?
Let's stop there, Jim. They have little effect on the 10-meter band, which is by the HF bands, but they have a lot of effect up at 2.4 gigs, which is the Wi-Fi band, and 900 megahertz. The higher bands, the weather will affect. The lower bands, it doesn't affect as much.
Okay, thank you. What weather condition would decrease the range at microwave frequencies?
Fog and rain.
Precipitation, yep.
That was the next question, yeah.
Yep. And that is the end of module 4A. Let me close that. And I just noticed that Robin shared a cool chart here. So here's another chart with kilometers and miles for the different troposphere, stratosphere, mesosphere, thermosphere and all your different layers. Oh, look at that. The balloon only goes up here. Your rockets go up there. Thanks, Robin. I'll
You're
send that
welcome.
out and I'll add that to the next email. Okay. Buy more books. Now comes the fun part. Antenna fundamentals, feed lines, and your favorite SWR. The antenna system. Antenna transforms current into radio waves, transmit, and vice versa for the receive. The feed line connects your station to the antenna. Test and matching equipment allows you to monitor and optimize your antenna system performance. The antenna, some vocabulary. The element is the conducting part or parts of an antenna designed to radiate or receive radio waves. The driven element is the element supplied directly with power from the transmitter. An array is an antenna with one or more element. Parasitic element are elements not connected directly to the feed line. Resonant, an antenna is resonant when its feed point impedance has zero reactance. The feed point is where the transmitted signal energy enters the antenna. Radiation is not radioactivity. An antenna emitting electromagnetic waves. Electromagnetic waves are radio waves are electromagnetic waves. Electric and magnetic fields are at right angles to each other, oscillating at the wave's frequency, spread out into space from the antenna, and are created by AC current. Wave and current have the same frequency. Wave polarization is the orientation of the wave's electric field component with respect to the Earth's surface. Vertical or horizontal is determined by the elements. Can be circular if the orientation twists as the wave spreads through space. Combinations of polarization are called elliptical polarization. Cross-polarization. Antenna and wave polarizations must match for maximum reception. Cross-polarized is antenna elements and the wave's electric field are at right angles. Can reduce the reception by a factor of 100. For elliptically polarized waves, such as HF skywave, any antenna will respond at least partially. The decibel, or dB. A ratio expressed as a power of 10 to make large numbers easier to work with. Minus dB, or the dB is a 10 log power ratio. dB 20 log is the voltage ratio. Positive values in dB indicates ratios greater than 1, and negative values of dBs are for ratios less than 1. Antenna gain is discussed in terms of dB. The antenna, some vocabulary. The gain is the apparent increase in power in a particular direction by focusing radiation in that direction, measured in decibels. Isotropic, equal radiation in all directions. Omnidirectional, no preferred horizontal direction. Directional is an antenna that focuses radiation in specific directions. Antenna radiation patterns. Radiation patterns are a way of visualizing the antenna's performance. And here we see the azimuthal pattern.
Jim, let's go back 2 slides.
Okay,
Yeah. Okay, the isotropic is like a soccer ball. It's radiating in all directions. And omnidirectional is like a balloon that's held at one end and it's going off in one direction. That gives you kind of a visual of what you're looking at. Isotropical antenna does not exist. It's an imaginary antenna, but it's like it's radiating like a soccer ball in all directions. And the omni is focusing one direction. Go ahead, Jim.
okay. Let me click on this here real quick.
I thought directional was focusing one directional. Omnidirectional is in multiple directions.
Yeah, and it's more flat. It's omnidirectional at 360, like in the horizontal range, and it's flat vertically, or it's like a wheel pointing up, and it's flat the other directional.
Okay.
Isotropical is like a ball. The omnidirectional is dead on either east or west or north or south on it.
Is the isentropic more theoretical, like the ideal case?
It is.
Okay.
You know what's confusing about that, Jim? Omnidirectional for a microphone is 360 degrees. You'd think that the omnidirectional would be the same for an antenna, but they're choosing not to define it that way.
An antenna, when they say omnidirectional, is like a bagel or a donut. It's round and large in one direction, and it's not large in the other direction.
Right. It's more horizontal, I guess you'd say. So
Yes.
Okay. So radiation patterns are a way of visualizing the antenna performance. The further the line is from the center of the graph, the stronger the signal at that point. The graph is calibrated in dBs. Radiation pattern vocabulary. Nulls are directions of minimum gain. Lobes are regions between the nulls. The main lobe is the lobe with the highest gain. Side lobe is any lobe other than the main lobe. Forward gain is the gain in the direction assigned as forward. I was just pulling my book to that part. So the two patterns are on page 4-8, and you'll see the description of the side lobes and the main nodes. That's on 4-8. Azimuth pattern is the radiation pattern showing the gain in all horizontal directions around the antenna. Elevation pattern is the radiation pattern showing the gain at all vertical angles from the antenna, often restricted to angles above horizontal. So here's the two patterns, the azimuth and the elevation. So the azimuth is looking from the top down, and the elevation is looking from the side, radiating up towards the top. Radiation pattern vocabulary. Front to back ratio is the ratio of forward gain to the gain of the opposite direction. Front to side ratio is the ratio of forward gain to gain at right angles to the forward direction. Feed lines. The purpose of a feed line is to get RF power from your station to the antenna. Basic feed line types is a coaxial cable, or also called coax, open wire line, OWL, which is also called ladder line or window line. Power loss as heat in the feed line is called loss, and it increases with frequency. Feed line vocabulary. Center conductor is the central wire. The dielectric is the insulation surrounding the center conductor. The shield is the braid or the foil surrounding the dielectric. And the jacket is the protective outer plastic coating. Forward or reflected power is the RF power traveling towards or away from a load such as an antenna. The coaxial cable. Most common feed line. It's easiest to use, not affected by nearby materials, has higher loss than open wire line at most frequencies. The air-insulated hard line has the lowest loss. Open wire line is lighter and less expensive than coax, has lower loss than coax at most frequencies, but is more difficult to use since it is affected by nearby materials, and requires impedance matching equipment to use with most transceivers.
And what they mean when they say affected by nearby materials, if you got to pass it out through a window or pass a door to get it to the outside antenna, the door will affect the signal going through the flat wire. It's like the old TV cables we used to have. Things around it do affect it.
Yeah, and you also want to keep it away from the metal poles. Characteristic impedance.
Katie, can you go back to that last slide? Can you talk about why the windows? What are the windows? Is it for weight savings or?
No, it affects the signal going through the. If you got a metal window, it affects the signal going through the window. A metal door affects the signal going through the door, and it disrupts the signal. It reduces it and it distorts it like that, puts it out of phase sometimes. There's several things that happen to it, but the signal going through a metal window or metal door is the issue, getting it outside if you get the window shut. You can shut the window on it fairly easy, but the things around that feed line are affect the signal going through it.
And Daniel, she was actually, I think, asking about the 450 ohm window line, why the little windows are in it.
The windows are there just to save material. It doesn't matter whether you have a solid plastic there or less material, it just saves plastic in there. It's a non-conductive material that separates the two wires at a specific distance. That makes the impedance.
And Katie, one of the reasons that other adjacent materials affect ladder line, it's called, or window line, is because there's really no grounded shielding around it. When you have coax, that grounded shielding protects it from being affected by other materials nearby, where the twin lead is much more affected by materials because it doesn't have shielding around it.
Appreciate the discussion. Thanks for clarifying.
You bet.
Okay. Characteristic impedance. The impedance presented to a wave traveling through a feed line is given in ohms and symbolized as ZO. Depends on how the feed line is constructed and what materials are used. Coax is usually 50 or 75 ohms. Open window line is usually 300, 450, and 600 ohm. Our favorite, standing wave ratio. If the antenna feed point and feed line impedances are not identical, some RF power is reflected back towards the transmitter. This is called a mismatch. Forward and reflected waves create a pattern of standing waves of voltage and current in the line. The SWR is the ratio of standing wave maximum to minimum, measured with an SWR meter or SWR bridge. Standing wave ratio is reflected power. The reflected power is re-reflected at the transmitter and bounces back and forth. Some RF power is lost as heat on each trip back and forth through the feed line. All RF power is eventually lost as heat or transferred to the antenna or load. A high SWR means more reflections and more loss of RF power, which is less transferred to the antenna or load. Now we have some videos on,
Jim, let me stop there.
okay,
If you have an SWR of and only 75% of the signal gets past it to the antenna, then 25% comes back toward the transmitter. Then that 25% comes back up, and again, it's only 75% of that goes through, and we've got a quarter of that's going to be 8% comes back down to the transmitter, back and forth. And this is why you have to match the impedance. When you match the impedance, all the energy goes through that transfer point onto the next issue. It comes out of you match the transmitter with the feed line, so you get all the power out of the transmitter, and you match the antenna to the feed line and get all the power out of the transmission line to the antenna to get into the air. And that's what the SWR is. If you got a perfect match, all the power gets transferred. If it's not a perfect match, then some of the power goes back and forth until it gets dissipated. Is that making sense? Okay, go ahead, Jim.
okay. So we've got a couple of, well, I've got 3 different videos, but I'll show just this first one here. Let me stop the share, and I need to redo the share, make sure to share the sound. Okay. Okay, let's try that again. Okay, hang on a sec. And now you should be able to see it. There we go. He does a real good job of describing everything with the little text.
292,
Now you can see in here how there's 2, 3, 4, 5, 6, 7. You'll be able to count the changing of the reflected energy, and the more reflected energy reduces areas and increases areas. So I'll go ahead and continue.
313, 335, 355, 376, 399, 419, 440, 461, 470, 483, 505, 514.5, 526, 557, 597, 643, 682, 723, 763, 771, 812, 857, 903, 948, 991, 1037, 1075, 1120, 1159, 1205, 1246, 1291, 1329, 1373.
So when you see the bigger points like that, those are the higher SWRs that are building up inside. So each one of those are high SWRs versus lower ones.
So Jim, a perfect 1.1 SWR would be flat.
The flat, yep. And higher SWR makes those little peaks and valleys.
We just had the most amazing family vacation.
Don't need to watch your commercials. So that is one of the, I'll send the other, there's a Mythbusters. Let me find sharing. Oh, it is still sharing. Or no, it isn't. Where's my controls?
Probably on the bottom.
Yeah, I had to make the screen bigger first. Okay. So the other videos I'll share. One of them is the Mythbusters, and then the bottom one is the older video that's that I saw when I was at Daniel's class. Geez, that was 5 years ago, 6 years ago.
Still a great video.
It is. So now everybody's making all kinds of little videos there, but I'll share those out. So nothing is perfect. A SWR equals the ratio of the feed point or load and a feed line impedance. Whichever is greater than 1, SWR is always greater than 1.1 to 1. What is an acceptable SWR? 1 to 1 SWR is perfect. There's no reflected power. Up to 2.1 and 2 to 1 SWR is normal. Modern radio modern radios lower transmitter output power for protection when the SWR is above 2:1. SWR above 3:1 is considered high in most cases. Erratic SWR readings may indicate a faulty feed line. I need to move this over. Faulty feed line connectors or a faulty antenna. High SWR can be corrected by tuning or adjusting the antenna,
which means either lengthening or shortening it.
or with an impedance matching equipment at the transmitter called an antenna tuner or trans match. It does not change the SWR in the feed line. Adjusting the SWR. An SWR meter is inserted in the feed line and indicates the mismatch at that point. Either adjust the antenna to minimize the reflected power or adjust the antenna tuner for minimum SWR at the transceiver. Dummy loads. A dummy load is a resistor and a heat sink. Is used to replace an antenna or other piece of equipment during testing. Dummy loads dissipate signals in the feed line as heat. Allows the transmitter testing without sending a signal over the air and is helpful in troubleshooting an antenna system. All right, test time. Practice questions. What can happen if the antennas at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization? Go ahead and unmute. The signals could be significantly weaker when they're at opposite ends and not using the same polarization. What type of wave carries radio signals between transmitting and receiving stations?
Electromagnetic waves.
Electromagnetic is correct. Which of the following results from the fact that skip signals refracted from the ionosphere are elliptically polarized?
They'll partially respond.
It's either vertically or horizontally polarized antennas may be used for transmission or reception.
Jim, one thing that's kind of useful, if you're putting up a vertical antenna, the downside of a vertical, even though it can work really well for the signal, it picks up a lot more terrestrial noise, because terrestrial noise like plasma TVs and whatever, they're vertically polarized. If you have a horizontally polarized antenna, it's a lot quieter. So just something to remember.
Yep. Move this out. What property of a radio wave is used to describe its polarization? That is the orientation of the electric field. What are two?
Jim?
Yeah.
On that one there, it's where the elements are pointing. If the elements are pointing up, then it's vertical. If the elements are pointing sideways, it's horizontal. That determines which way the electrical field is. The magnetic field is opposite, but it's the way the elements are pointing. The wire's pointing up, the wire pointing horizontal. That's vertical or horizontal.
Okay, yeah, and that is shown on figure 4-4 on page 4-6. You see the two different ways of horizontal and vertical. What are the two components of a radio wave?
Magnetic and electric.
Correct. Magnetic and electric fields. What is the approximate amount of change measured in decibels or dB of a power increase from 5 watts to 10 watts? Power increase. This is a 3 dB change.
And that's
Daniel?
a plus 3 dB.
Yeah, plus 3 dB. Didn't you have a little trick to remember in the dBs?
3 is a 2, 4 is a 6, 10 is a 10.
Yeah,
3 decibels is double or
double.
half.
Yep.
Half of it's minus. 6 is 4 times, and 10 is 10 times.
Yeah, I couldn't remember the little
The
catchphrase.
song, yeah.
The
We sing a
song that
song
we,
that way.
yeah.
3 is a 2, 6 is a 4, 10 is a 10.
Yep.
Daniel, is that in any book?
That is not in any book. LW come up with that about 8 years ago, and we've sang it in our classes ever since. Over 2,000 people have sang that song.
Yeah, but I couldn't remember the words to the song, but I could hum it.
3 is a 2, 6 is a 4, 10 is a 10. Decibels to the ratio.
Jim, when you send out those charts on the ionosphere, I sent you a second one. Maybe you could include that little ditty. That's pretty helpful.
Okay. Yep. What is the approximate amount of change measured in decibels of a power decrease from 12 watts to 3 watts?
It's decreasing, so it's going to be negative.
Negative.
If you cut it in half, you'll get 6 watts. You cut that in half again, you'll get 3 watts. So 2 times 2 is 4, or 12 divided by 3 will give you 4. So what's the ratio?
6.
It's 6 minus 6 dB. Yeah, minus 6 means it's going down, and it's a fourth the size.
And that's on page 4-8. What is the approximate amount of change measured in decibels of a power increase from 20 watts to 200 watts?
200 divided by 20 is going to give us 10. So it's going to be 10 decibels.
dB. A radio wave is made up of what type of energy? That would be electromagnetic. What is the primary purpose of a dummy load?
It's for testing, making tests where you don't want to broadcast on the air.
Yep, to prevent transmitting signals over the air when making tests. What, in general terms, is standing wave ratio? That is a measure of how well a load is matched to the transmission line. What reading on an SWR meter indicates a perfect impedance match between the antenna and the feed line?
1-to-1.
Yes.
1-to-1, correct.
100% in, 100% out.
Why do most solid-state amateur radio transmitters reduce the output power as the SWR increases? That is to protect the output amplifier transistors.
Remember we said the signal goes back and forth between the antenna and the transmitter? Well, that creates heat at the transmitter side, which is the problem. And it can burn up the finals in the transmitter. So we want to reduce that, so it reduces the power out.
And that's true not just of amplifier transistors, but the old stuff that was tube had the same issue.
Yes. And that's why you want to match it, match it, match it, match it.
Yep. What does an SWR reading of 4 to 1 indicate?
A mismatch, impedance mismatch.
An impedance mismatch, correct.
And the larger number always comes first.
Okay. What happens to power loss in a feed line? What does a power loss do in a feed line?
Goes to heat.
Yes.
It is converted into heat, correct. What does a dummy load consist of? A big resistor and a heat sink. I should have brought one in.
You know, in the old days, back in the 60s, we used to use an electric light bulb incandescent as a dummy load. It wasn't perfect, but it worked pretty good.
Which of the following describes a type of antenna loading?
Don't have the answers there.
Yeah, I
So
don't have the answers. Inserting an inductor in the radiation portion of the antenna to make it electrically longer. What is the gain of an antenna? What does the term gain of an antenna mean? The increase in signal strength in a specified direction when compared to a reference antenna. Why is it important to have low SWR when using coaxial feed line? That is to reduce the signal loss. What is the impedance of most coaxial cables used in amateur radio stations installations?
50 ohms.
50 ohms is correct.
the reason we use 50 ohms is a dipole is normally 70 ohms and a vertical is 35 ohms.
Why is coaxial cable through coaxial cable is increased?
Loss increases.
Loss increases, yep. Cause erratic changes in SWR readings. A loose connection in an antenna or a feed line. Sorry, I kind of hit that one fast. My other laptop was flashing internet issues, but I don't see anything. Okay. Which of the following types of feed line has the lowest loss at VHF and UHF? And it doesn't show the types. The air insulated hardline is the lowest loss. Actually, there's a chart. Where was that? That was on page 4-9. Oh,
It's on
no.
4-10
There it is. Yep.
or 4-9.
Yes, but which one is the air?
So they don't show the air, but it essentially,
What the air is has air in there. It has a kind of a spiral plastic insert that goes between the outer shield and the center wire that holds that center wire in the center of the opening. But it's mainly air. It's got a little plastic that spirals down across to the center connector.
Okay.
Oh, and that's the end of module 4B. And that is the end of all of the modules for tonight. If I'm correct here.
Yeah, we got through at 9:11, Jim.
Yeah, 4A and 4B. So that's everything for tonight.
That's okay, Robin. That's good.
So, any questions or thoughts? Do you guys want to see the other 2 videos for the standing wave?
As long as you have popcorn to service, yeah.
Sure.
Let me find it here. Feed lines. Okay, there's our SWR. Okay. Let me pull up Mythbusters. I'm going to skip the commercial here. Okay. Share with the sound.
In Voice Flame Extinguisher, Adam and Jamie investigated the viability of fighting fires with sound waves. But what we didn't have time to show you was when they explored another fire phenomenon, the Rubens tube.
This is a stunning visual representation of a sound wave.
Yeah, let's fire it up and see what it does.
All right.
It's a classic physics experiment that has recently become an internet phenomenon. A length of pipe is perforated along the top and sealed at both ends. One seal is attached to a small speaker, the other to a supply of a flammable gas. The pipe is filled with the gas, and the gas leaking from the perforations is lit.
Oh, it's beautiful.
So this is called a Rubens tube, right?
Yep, it's Rubens tube all right, and what you're seeing is a standing wave rendered in fire. This is how it works. When the guys play a tone through the speaker, the sound wave enters the tube, and the confined space creates reflections and interference, which combine to create a standing wave. The standing wave affects the air pressure inside the tube, which affects the amount of gas coming out of each perforation, which affects the size of each individual flame.
And what we're looking at is areas of higher and lower compression being made by the sound waves down the tube, affecting how much gas comes out of each hole.
If you keep the frequency constant, you can determine the wavelength by simply measuring it with a ruler. And if you think it looks familiar, it probably is. Rubens tubes have been around since 1905, when Heinrich Rubin fired up the first.
Look at that. Yeah, we're watching the waves pile up. Yeah, totally.
That worked.
That is very, very, very cool. I had not imagined that there was such a clear visual representation of a sound wave.
Okay, now I'll show you the original one that I saw. Nope, hang on. I'm going to reshare it.
Now, I really want to bring it down, but it involves open. Let's do a classic physics experiment called the Rubens tube. Now, I really want to bring it down, but it involves open flames, and some people have issues with open flames. So, what we have here is a length of PVC pipe, has about 100 or so holes drilled at half-inch increments, got some foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of this 2-inch tube. On that side, we've got some lab tubing leading to some propane. So let's fire it up and see what it does. All right, as you can see, we got some nice standing planes, a little bit of oscillation from the vibrations in the hose. Let's throw some sound in there and see what happens. Let's start with a 449 hertz frequency.
Notice the little flame on the right side that's left over. Go ahead, Jim.
As you can see, this sets up a standing wave, and we can see, well, the emerging sine curve that represents sound. What happens here is we're having the sound compressing here and not compressing here. The lower pressure here allows more gas to escape into the atmosphere, shaping the sound curve.
Go ahead and stop it there, Jim. If this tube was a little shorter, the flames would be a little higher and there wouldn't be any wasted energy at the end. That's called the SWR, the reflected power. Go ahead, Jim.
Now, if we change the frequency,
go ahead, one more. There. You see there's no flame left over on the right side, and the flames peaks are higher. That's what you want in your antenna. That antenna that tube is designed for that frequency to get the maximum energy out of it. And there's no SWR. That's a 1-to-1 ratio right there. Go ahead.
we can see each time we set up a standing wave, we get that sine curve. Higher the frequency, the more waves. Now let's throw some music at this. How about some Dave Brubeck? Now we have real life sound visualization with fire. Now Dave Brubeck isn't terribly energetic, so let's try something a little more energetic. Now that's some good physics. I'm going to turn off the gas and have some fun. And that's a Rubens tube.
And that's just 3 of the Rubens tubes that I found on the internet. So I'll share those if you want to share them with your friends and stuff. Pretty cool.
Did you see how the length of the tube or the frequency made a difference on how high the flames were? That's what we call matching. That's what they call the 1-to-1. And if you have more than one sine wave there, that's a harmonic of the basic frequency. So some of his tubes were about 4 times longer than the original frequency, but you had nothing left over. So all the energy was getting off the antenna. One antenna will look like 40 meters, will also work at 15 meters.
Don't play with fire at home. I like how he was doing it in the garage there to keep from not messing things up.
So Daniel, the higher the SWR with that kind of a setup, that means would that mean the more unburnt propane goes into the air?
No, you're gonna have a flatter flame. If you're matched, you're going to be up and down, and there's going to be little left over. It's going to come back down to a bottom point on the flames circle.
Oh, I was trying to relate it SWR and a feed line. The higher the SWR, the higher the heat loss.
Yes. The more energy is not getting off to the antenna is going to be burned up in the. It's going to be like the heater wire of your toaster. It's going to heat up the feed line.
Right. Okay.
So any questions or comments on chapter 4? Guys made it through record time on that one.
That was a very important section, guys, kind of understanding the antenna, the feed line, matching them, the SWR, a lot of important concepts in there. If you didn't get it the first time, ask questions,
Yeah.
please.
No, the only dumb question is the one that you don't ask. So, chapter 5 is all about the radio equipment, modulation, transmitters and receivers, digital communication, power supplies, and batteries. This next, so there's 10, 20, 30, about 45 minutes of videos and 19 pages. Do we want to continue doing them one chapter at a time, or do you want to try to add 5 and 6? There's a little bit more, 24 pages in there.
One at a time is good.
What was that?
One at a time is good for me.
Okay, we'll just keep it at one then. So next week will be chapter 5. I'll add in the videos, and there's a couple of JPEGs that Robin sent for the Ionosphere 1 and 2, so I'll add those in too. And I'll post the videos up on YouTube for review if you need to. So if there isn't anything else, I'm going to go ahead and
I got
stop.
one question yet, Jim.
Sure.
Just a thought process here. There was some discussion about setting up the tests, somebody setting up the tests, whether it be an organization or whatever. Any indication when they're going to have the testing for the month of March, April, what?
We have tests weekly at this point.
Oh, really?
And we'll have more available in March.
Yeah, and this Tuesday we'll be having the Mike and Key board membership board meeting, and I'm going to talk to Scott and give him a heads up and see where his scheduling and stuff is. So yeah, soon to come. But if we do one chapter every week, we've got 10 chapters. So we're almost at the halfway point. So I
think it's chapter 10 is on safety. That seemed to be a pretty short one, but
yeah. So on that one we can go and in addition to safety, we can do some practice test sessions through the Zoom. Go through a couple of sample, what it would look like for your 35 questions. We can answer them as a group, see how we all do.
Maybe Elaine for next week can tell us what her SWR is of her piano. So
Watch it.
It'd be neat to have you play a tune for us, but I think that's forbidden on the amateur radio airwaves, isn't it, Daniel?
Yes, but not Zoom.
Yeah.
All right, Elaine, you pick a song.
All right.
After we pass the test, we'll celebrate like that.
There you go.
Sounds good.
Okay, I'm going to stop